is by Juan Manuel Burgos. And what is your title?
That doesn't matter, it's okay. Thank you very much. And it is, yes, it doesn't matter. Well, thank you very much. And this work came, we made a funny question to ourselves with Alberto Berkowski, what an inverse limit of toric varieties should look like. The work is not ambitious at all, it is just a funny question. I think it's a funny work, and I hope that you get funny with the results. Well, let me start with a couple of examples that motivate this work. Well, first of all, it is with Alberto Berkowski. Work in progress. Well, example 0, it's a kind of definition notation. Example 0, it is most a convention about the notation I will use along the talk than a definition, but it goes like this. Take the divisibility net and put some puncture complex planes in there. This is in position M, this is in position N, and whenever M divides N, I will put here this map. It's the map that makes M divided by M foldings around the puncture plane. And this defines an inverse system. The inverse limit of this, we will denote it by this. And some remarks. First of all, it is a fibration. If you take the first coordinate in the inverse system, the canonical projection, you get that this inverse limit is a fibration over this, with fiber the adelic completion of the integers, the profinite completion. Other remark, it is a lamination. It's a lamination a minimal lamination by densely immersed copies of the complex plane. And well, example 1. Make the same construction, but taking the Riemann sphere instead, and take the inverse limit. Define this as CP1Q as the inverse limit of Riemann spheres. Well, now you don't have a fibration because the morphisms, these finite coverings, will ramify in the poles. And what you will have instead is the suspension of the adelic solenoid. Topologically, I will draw it instead of writing what it is, just to get the intuition. Here you have the adelic solenoid, and topologically it is the suspension. So you have two cusps in here. Okay, example 2.
Can you use the board above as well?
Yes, thank you. I am not used to this technology.
So,
Well, example 2. Do the same with the CPN. Inverse limit, CPN. Now you do the same construction as example 0. I don't know if you can see it. In each homogeneous coordinate of this. And then you take the quotient by the diagonal action and you get the inverse limit. Another thing I didn't say about example 1 that is interesting is that because I have now topological constraints in here, the points, they don't look the same. We have cusps. When you want to calculate the automorphisms of this inverse limit, it won't be like CP1 that is PCL2C, because you only can map the cusps among them. You will have an involution in there. So this will be a subgroup of that. It will be C star Q semi-direct with zeta 2. And zeta 2 is the involution that permutes the cusps. Instead, the automorphism group of this, of CPN Q, will be quite similar. It will be the all the n+1 diagonal square matrices with this n tracing here, and take the diagonal action, the projective, and semi-direct with the symmetric of the cusps in here. Okay, and example 3. Take instead the weighted projective space. CP12, for example, take its inverse limit as before, and calculate its automorphic group. It is not quite easy right now, because now the cusps are homeomorphic between themselves, but the leaf structure of space is quite different. So you don't have the involution as in the previous case. You won't have a map that is globally defined and permutes the cusps. So the automorphism in here will be just C star Q. And this motivates the following questions. Well, first question. Can we generalize it to toric varieties? And second question, how to determine which cusps can map among themselves and which do not? Because we saw the problem that which cusps map among themselves, it's a global problem, it is not a local one. The cusps, locally, they look all the same. So, let me recall a very basic thing about toric varieties. If you have a cone, let sigma be a cone, define S sigma as the dual semigroup of that. Gordon's lemma. This is very basic stuff. Gordon's lemma. S sigma is finitely generated. And define the affine variety as follows. Okay. Now take a fun. But instead, see it as a direct system. With the inclusions, respect to the canonical inclusions. Then the toric variety associated to that fun will be the following. You will have the fun is a direct system. Then this will define an inverse system. And when you apply this, the home functor, the contravariant home functor, you will get again a direct system. So you have this direct system in here. and the direct limit is your toric variety. Your toric variety with C points. But the key point is that I humbly think that the right way to see a toric variety is not specifying its points. It's just to see it as a functor. So I will see the toric variety as this functor. It is always presented with the C points, and a good reference to see where they emphasize the functorial aspect of toric varieties is the paper of Lupercio, Katsarkov, Verkhovsky, and Merseman towards a definition of non-commutative varieties. And when you see the toric variety in this way, then it is pretty natural to define the inverse, to define the respective lamination as follows. Instead of taking ordinary C points, I will take these points in here. So a toric variety, I have this structure and I choose what points I will fill in the structure. That's the main idea. And an immediate property is the following. Recall that this is the inverse limit of C. And because the inverse limit commutes with the home functor and with the other limits, I will get what I wanted, the inverse limit of toric varieties. So this answers our first question. What is the inverse limit of toric varieties? Well, it's just apply this functor in here to this kind of laminated points. So let's see what about the second question, how to calculate the automorphism group of that. Well, define this mapping here. First, a couple of definitions first. Let n be a lattice and m it's dual lattice. Define delta 1 as the set of rays, set of one-dimensional cones, and define the following map. Define the map as follows. Here I'm taking the respective generators of the rays, and this is the natural pairing. Define G as the kernel of G. We have this alternate description of the toric variety. I just write it to understand the automorphism calculation. Define the following map. The group, the symmetric group of the rays, the group permutating the rays to the automorphisms of G. And define it as follows. For every permutation, define this automorphism. Just to explain a little bit of notation, I am seeing this as a functor in this variable in here, so it makes sense to define it that way. So define the symmetry of the fan as follows. Salud. Como symmetry of the fan. Then then this will be the group that that permutes the cusps. So I have the trivial part, and this is the group that describes how the cusps are permute among themselves. And well, that answers the second question. And let me comment a third question I didn't wrote in the beginning. How is the vector bundle category over the laminated space? And it is quite easy because if you have a classifying map like this, on the Grassmannian, the Grassmannian, then it's a theorem in. I just wanted to say that it was an archive, but it is not. It is still not in archive, so it's a theorem of us that you can always find a finite level in the inverse system, such that this commutes up to homotopy. These two commutes. So you have that the category of vector bundles of rank L over the laminated toric variety is the direct limit of the usual ones. And this is another proposition. And as a corollary, you have the same thing with the K-ring. And I was wondering, I believe it's wrong, but maybe it's a catch. Maybe there is a catch in the argument. But I was wondering the following: if you have this direct limit, and you have that it's very easy to show that it holds for the coherent shifts in there. The same thing. And the same thing will happen with the bounded category. And take, for example, the CP1 case. You have that. That this is the bounded derived category of the representations of the Kronecker quiver. So I was wondering, there is a way of seeing this in the case of CP1Q, the derived coherent category of CP1Q as the derived representation category of some algebra in there. I don't know. I don't think that the functors in there translates to some end of functor in the derived category. I don't know. It's a question. It's an open problem for you. So maybe it makes sense. Thank you very much. Everyone is hungry.
Well, thank you very much. The event is over.